test and complete that worksheet and turn it in with the next part of housekeeping. Okay, and so the next part of housekeeping is test corrections. And for test corrections, all right, you can correct the ones you missed for half credit. Okay, now here's the rules, all right. One, use the paper copy of the test, all right. It's returned to your file folder upstairs. Okay, the paper copy that you had in class, even if you didn't use it, it's returned there. So you have a paper copy already. Get it from the filing cabinet. Marissa's filing those right now, I think. She was instructed to. So just to let you know that. All right. So I want it completed on that. If you need more space, just flip it over, put it, on back, and complete the answer there. Cool. All right. Now, 2. Explain why it's incorrect. All right. Why your answer was incorrect. 3. Give correct answer. All right. Now this is really important to me. If it's a math problem, okay? If it's a math problem, show all work with, guess what I'm gonna write right now? All right, if it's not a math problem, give correct answer with explanation. Okay? Now, in addition to that, I want a reference. Okay? And I prefer the textbook. All right? I want a reference of the section where that topic is talked about. Right now, I don't just want you to go find the reference. What do I want you to do? Read and study that section because you missed the problem, right? I'm trying to get you to open your test book to where you missed the problem. That's in fact, out of all of these things, in my mind, this is the most important part. Okay? Now, when you're doing this, all right, I would prefer complete sentences. Okay? I don't know if there's sometimes that you don't need complete sentences. You with me? So I know that, but where possible and where it's appropriate, then when you're writing out that answer, write in complete sentences. Cool? Does that sound reasonable? Is that worth it for half the points that you missed? Right? So if you have a 70 on the exam and you appropriately answer those correctly, right? That means you missed 30 points. You could gain 15 of those back and you could move from a C to a mid-B. It's reasonable, isn't it? Okay, so I'm giving you that opportunity. All right, please take it. All right. Plus, in addition to that, you can get 5 points extra credit, right? From where? From the chemical nomenclature worksheet. And it's really not that hard to do. You guys already have this skill. You're going to smoke this thing, right? You'll be able to just go down through there and name the correct names for these compounds. What's the first one? Iron, and then there should be a Roman numeral 2. It's a Roman numeral 2 in this case, and then hydroxide, yeah. So that would be the formal name for that. So there, everybody, I gave you one. Done. Cool? All right. Okay. Any other housekeeping?
Are you going to tell us what we got wrong on the test, or just going to figure it out?
You can go in and we'll show you the questions that you got wrong. It won't tell you the correct answers. Yeah, that is correct, isn't it? Yeah, it will show you the ones that you missed when you log on to Campus Web and reopen that assignment. Okay, so yep, go ahead.
When do you want that stuff?
1 week. Oh, I should have wrote that on board. Thank you very much. I appreciate that. So that would be next Wednesday. One week. Just, beginning of class, we'll just make a file up here and turn it in. All right. Comments or questions on that? All right, empirical formulas. We stopped last time and we were talking about how many grams of methane can be formed from 100 grams of carbon. And we worked out that problem and we found it to be 133.6 grams. Okay, pretty sure we finished that. And so I did not start empirical formulas, that we're going to today. And so empirical formulas are the lowest whole number ratio of 2 or more combined elements, all right, in a compound. So we use empirical formulas often to find molecular formulas, and we'll talk about how to do that, all right? Chemical formula is either the same as the empirical or a whole number multiple of that. And so anyway, but all of this is whole number. This is an example. It's looking at 20 grams of carbon. And so that 20 grams of carbon is found with 8 grams of carbon, 1.34 grams of hydrogen, and 10.7 grams of oxygen. Now, to get to the empirical formula from that, we need a mole ratio, okay? And so that means from masses, we need to go to what? Moles, okay? Because we want a mole ratio. And so if I have 8 grams, 8.00 grams of carbon, I need to convert that to moles. What am I going to do? Multiply that times 1 over the atomic weight, 12.011 moles and grams. And so we have it up there equals 0.666 moles of carbon. Then the next one is 1.34 grams of hydrogen, right? And so 1 mole over 1 gram. Should put some sig figs on that. 1.0 grams, 201 grams for hydrogen. And then the last one, 10.7 grams of oxygen times 1 mole of oxygen over 16.0 grams. And so when I multiply these out, I end up with the moles of each. All right, so now I have the moles of each. What I've actually calculated, whether you know it or not, if I take this and write a formula, this is C 0.666, right? H 1.32 and O 0.699. But what are those numbers? Do we use fractional numbers in describing the mole ratio of a compound? No, because we don't have fractional atoms, right? And so because of that, we want to convert these to a whole number ratio. So what I do is I pick the smallest, right? I take the smallest value and I divide that into all the values. Okay, can you guys do that? And so when I do that, if I look at these 0.666, I think I did that one wrong, I inverted the 6. And divided by 0.666 divided by 0.666. And so this is approximately equal to what? 1. This is approximately equal to 2. And this is approximately equal to 1. And so C1H2O1. Now, if we write this appropriately, it would be CH2O because we don't show the ones, right? You guys with me? So that is the empirical formula for that compound, okay? Now, the way that's written, I automatically see something. What would we call that compound? It's a carbohydrate, right? Just catch that? CH2O? No, it really is. I mean, yeah. It wouldn't have to be, but yes. All right. Now, yes?
Why would, I probably missed it, but like, why would you have a condom?
Because I'm looking for a whole number ratio between these. And so I'm getting at least some of the digits to whole numbers. Now, what we're going to find is they don't always end up to be whole numbers. In fact, if we go down a few slides, right here, what we find is that if we have fractional endings to those after we do that division, then this is the multiples. Okay? And so we're looking and we're going to see an example of 0.67 in one of our examples coming up. Okay? Where that and 0.33. And so anyway, but right now, using the definition that we talked about for empirical formula, what I want you guys to do is identify or make these into empirical formulas. So if I'm looking at the first one, it's giving me the relationship that we had right here, right? Before we did that division, it's got that relationship. So if I'm looking at BO1.5, what's the empirical formula for that compound? What do I need to do to that to make those two whole numbers? Multiply, well, I would multiply both of them by 2. Right? If I multiply each of them by 2, what does 1.5 become? 3. And so that first one is B2O3. Okay, you guys with me? If I look at the second one, now it's actually written in multiples. What's the empirical formula for B? CH, right? Because I would divide both by 6 to get to the empirical formula. You guys with me? All right. What about the next one? NaPO, Na.5, P.25, and O. So if I multiplied all of them by 4, what would it be? Write it down on your paper. See if you can get that. It is sodium phosphate, yeah, exactly. So how many people got to Na3? Oh, no, that's wrong. Na2PO4, which is interesting because, no, that wouldn't be sodium phosphate because why? How many sodiums are there? There's only 2, and phosphate has a charge of what? -3. So either that's an error, right? Or we've got something weird going on. Okay, so that wouldn't be a compound that should be made, right? How about the last one? How about the last one? If you multiply by 3, what happens? Multiply them all by 3. See what happens. First one I got, it's 9. The next one's 8. Yeah, would you guys agree with that? And then what's the last one? 4. So if we check that, then C9H8O4. So it's all multiples of, there's a little bit of test in C, right? Or, as I showed you, you could learn this table. Okay, it might be helpful. And so this gives you the multiples. When I have a 0.2, it's times 5. When I have a 0.25, it's times 4. 0.33 times 3. 0.4 times 5. 0.5 times 2. 0.67 times 3. And we saw those, both of the 0.33 and 67 in that example. And then the last one, 0.75, is times 4. And so that takes all of those to whole numbers. Okay? Now, sometimes when I have 3 things, do I have to go to bigger amounts? So, yes, and the answer is yes. Sometimes, like if I have a situation where I have a 2 and a 4, then I might have to go to the 4 for the 2, right? So, all right. So, let's try this idea from this table, those multiples, and you guys write the compound. If the mole ratio is 1 to 1, write down a compound AB. Write a compound AB that's 1 to 1. Now write down the AB compound that would be 1 to 1.5. Be 1 to 1.5. And the AB compound, that would be 1 to 1.3. And then the last one, 1 to 1.2. When you just have 2 things, you just start multiplying the fractional one till you get to a whole number, and then use that number to multiply times the 1, right? You guys with me? The second one is 2 to 1, or 2 to 3, excuse me, A2, B3, that's B. C is 3 times, right? So that would be 3, and what's 3 times 1.33? 4? Yeah. And then the next one is 5. So A5, B 5 times, that would be 6. So AB, A2. So you notice I'm doing those in my head, right? Do I occasionally have to get a calculator out? Yeah, I admit. Check myself. Okay. So, you guys good with empirical formulas? This fashion? Yeah. Doing it by mass. So, to do that, from fractional data, we have a different technique. Okay, not different, it's the same thing. We're going to do the steps that we did earlier and find the ratios. But you're going to take, if you have the percent composition by mass, then assume a 100 gram sample, then from there we can actually find the mole data, the mole ratios, and then from the mole ratios, then we can divide those to find the whole number ratio, divide and multiply, and then put the superscripts in the compound. So let's practice one of these, so we've warmed up for it. And so determine the empirical formula of a compound that has a percent composition of 43.7% phosphate or phosphorus and 56.3% oxygen. So what we're looking for, what this question is asking for, it's asking us to find X and Y, right? And it's giving us a starting place. And so when we start here from this point, then if they give you the percents, assume you have 100 grams, right? The whole pie is 100. each piece is 43 and 56% respectively. So if I turn that into grams, then I can make this 43.7 grams of phosphorus and 56.3 grams of oxygen. And so if I have them in gram amount, right, for the compound, then I can get to the moles, right? So I want you to convert those to moles. So you guys convert those to moles. What is 47 divided by 30.97? Or 43, excuse me, 43.7. 1.41. All right, so we got the bottom one. What's 56.3 divided by 16? 3.5, 2 moles of oxygen. So that means that we now have X and Y, and we have P is 1.41, and oxygen is 3.52. But I want to make those whole relationships, right? So what am I going to do at this point? Divide each by the smallest, and so that's 1.41 and 1.41. I got this one, it's equal to 1. And this is equal to 2.49. Now I'm going to ask a quick question. What is 2.49? It's really 2.5, isn't it? You guys with me? And so what do I do to get, so I'm going from here to here, right? This is how I got to this, through this step, right? Now to go to the whole numbers, then if this is 2.5 and this is 1, what am I going to do? Multiply by 2. So 2 and 5, so the answer to this problem is P2O5. Cool? Is that a nice walk through step by step using some tools that we already have, the percent composition, and then using the conversion to moles, and then adding in a ratio step. That's all we did. We added in a ratio step. You guys see how chemistry builds? So we're doing pieces of this, and then we're taking those pieces and putting them together to do a bigger thing. Okay? So this just walks us through that. This shows that first step to get to the P1.4 to O3.5. And so once we got to that, then we divide each of those by the smallest and then multiply them by 2. And so we got to P2O5. Fun? Yeah. So we're going to make even more complex problems. All right, but we're going to talk about this just a little bit more first. All right. I say more complex. No, just a different direction. Just the same complexity. So ionic compounds, right? Well, most of those are identified by their empirical formulas. Okay? Organic compounds are usually identified by their molecular compounds. Okay? Just be aware of that. And even some polyatomic ions, now if you notice S2O8, that mole ratio could be reduced to what? S2O8 could be reduced to 1 and 4, right? And so we report these sometimes, right, as more than, because those exist in their structure as covalent, but they have a mismatched set of electrons, so they're an ion. And so we still report them in that fashion, right? And when we have covalent compounds and we have the empirical formula and we know the molecular weight, we can find that ratio from that. And we're actually going to do some of those problems. So just hang on when we get there. Here it is, molecular formulas. And so we're going to determine molecular formulas. They're the actual number. So the empirical formula is P2O5. If I had P4O10, right, then that might be an example of a molecular compound if it existed in that fashion. So it's some multiple of this to get there, okay? So just be aware of that. I just had that one on the board. There's one on the board right now that we've actually used today. What's the empirical formula for glucose? It's in the middle of the screen up there. What's the empirical formula for it? No, that's the molecular formula. What's the empirical formula? The lowest whole number ratio. CH2O. Glucose is called what? It's a sugar. Sugars are called carbohydrates. Carbohydrate. You guys see where I said that earlier today when we were talking about that empirical formula? That's where it comes from. Okay, that relationship. Cool? Yeah. So anyway, so the molecular formula for glucose is C6H12O6, but the empirical formula would be CH2O. Right, just to give you the difference. Here's two examples. What is the empirical formula for both of these compounds? CH, right? CH. And so the same empirical formula, CH, right? Same percent composition for each of those. But we have two. Now, are those compounds the same thing then? They have the same empirical formula? No, those are two completely different chemicals. That's why we use the molecular formulas for organic compounds. You guys with me? Now, when I have sodium chloride, if I have 10 of those, then the crystal just gets bigger and I still just have the empirical formula combination of NaCl. And so in those we use empirical formulas in salts. All right, so this is acetylene and benzene. All right. So if I have an empirical formula and I want to find the multiplying factor to get to the molecular formula, so I'm going from empirical, the lowest whole number, right, to the molecular ratio, the molecular formula. If I have the molar mass of each of those, okay, I have the molar mass of each of those, and I divide the molar mass of the compound by the empirical formula molar mass, then I can get a multiplying factor, okay? And so then you would multiply all the subscripts to get to the molecular compound. So let's try that. Now this problem is the same problem we have on the board. We just have to go one step farther. Okay? So same complexity. So I want to do a mass balance with you very quickly. If I add 4.86, 38.57, plus 28.90, I get 72.33. Why am I saying that? So mass balance statement, why did I say that? Because these aren't given in percentages, are they? Could I start by calculating the percentage? Or if I have all of the elements of a particular compound, can I just take those grams and calculate those to moles and then use that mole ratio? Won't it end up being the same thing as if I went 2%? Yeah, so I'm just taking a step of I'm telling you, you can take a step of calculation out here if you recognize that, okay? But, so what are we going to do? How are we going to get to the molecular formula? We're going to start by finding the empirical formula, okay? So you guys need to find the empirical formula. How do I do that again? I've got, well, what's the elements we have present? Carbon, hydrogen, and oxygen, and we're looking for X, Y, and Z, aren't we? And we're looking for both the empirical formula and then the molecular formula. But what we're going to do, let's kind of figure this out. We've got the mass of the compounds, right? The mass of each of the elements, the mass of the elements, all right? And so if we have the mass of the elements, where can we go? Through the atomic weight, we can go to the moles, right? And from the moles, we can ratio to, what's here? Empirical formula. And then from the empirical formula mass, right? We can go to the molecular formula. Cool? No? Yes? All right, so we're starting then with carbon, hydrogen, and oxygen. And you're working that way. You've got 4.86 grams of carbon. You've got, oops, no, that's hydrogen. My bad. Has anybody ever done that on a test? And finished the answer that way, pulled the wrong number, multiplied it out? I do that occasionally. 4.86 grams of hydrogen and 38.57 grams of oxygen. I need to convert that to what? Moles. All right, I'll let you guys work. What's the carbon one? 2.34. What's the hydrogen?
2.4 on the top one.
Oh. What's the second one? 4.82. What's the third one? 2.4. That one's pretty easy to see right now, isn't it? What's the whole number ratio? I divide by the smallest, 1, and what's 4.8 divided by 1.4? So 1, 2, 1. So that's, now we have X, Y, and Z. C is 1, H is 2, O is 1. It's another carbohydrate, isn't it? So let's find that whole, or find the ratio of the two. How do we move? So we've got the empirical formula. We're right here right now. Okay? And we need to move to right there. What's the next step? A molar mass of the compound over the empirical formula mass. And the molar mass of the compound is given up there. So molar mass, empirical mass. All right. So that equals 60.05. Did I do this in my head? 12 plus 4, 16. Right? No, 12 plus 2, my bad. 12 plus 2 is 14, plus 16, 30. How many people got 2? Yep. And so what do I do with this 2? I multiply it times the empirical formula. Okay? So our final answer, the molecular formula, is C2H4O2. I did the molecular formula up here when I was doing my counting. I did this problem earlier. Cool, can you guys handle that? So we just added one step onto that to get from grams. Now if I had given you the percent hydrogen, carbon, and oxygen, could you have done the same thing? Yeah, because you could have gone from the percent assumed 100 grams and just converted that to moles and going on, okay? So don't make those harder because you're starting with the percent. All right? So anyway, so this is all the steps to get there. All right, in the real world, we actually do this math. All right, there's an analyzer called a combustion analyzer, and it's to determine the amount, used to determine the amount of carbon and hydrogen, or carbon, hydrogen, and oxygen in organic compounds. Okay, and so that carbon analyzer converts the carbon with excess oxygen to CO2 and water. Okay, you guys with me? And so it's easier to see in this picture in my mind. So if you look up, you guys see the combustion chamber? Yep. See the combustion chamber? And so if I put an excess of oxygen in there, then it will take my carbon, hydrogen, oxygen containing compounds and make them into CO2 and water. All right? And so there's traps, and those traps have an absorbent for H2O and an absorbent for CO2. Okay? Now, generally the way those work is they're packs, and you have a standard amount of compound you put in the oven, and your packs would have the correct amount of reagent to trap that. You would have the initial weight of your packs and then the post-combustion weight. And you would do it by mass. So you would be able to determine how much CO2 was made by a change in mass and how much water was made by a change in mass. Does that make sense? You guys with me? Yeah. And so, now wait a minute. How can we measure oxygen too? Well, we're going to have to do some stoichiometry. Okay? So we don't directly measure the oxygen. We're putting in extra oxygen, right? Because we're giving the system extra. So what we have to do is take our original mass amount, right? And subtract from that the mass of the carbon plus the mass of the hydrogen, which we find through stoichiometry. Okay, you guys with me? So let's do a problem because it's easier to see when we do that in my mind. Now, here's two equations that they're just showing, and these are equations you guys can already do. Okay? And so this is just looking at taking the mass of CO2 from the trap, right? The mass that we find from the trap, and or dividing it by 44, the molecular weight conversion, and then a mole ratio, 1 carbon to 1 CO2, and then multiplying times the atomic weight of carbon to get to the mass of carbon. Okay? The next one is to do the mass of H2O, and it's the exact same type of expression. We find the mass of the atomic weight of H2O, or the molecular weight, and then the mole ratio, and then times the molecular weight, or the atomic weight of hydrogen. Boy, I get that backwards there. So anyway, resulting mass is then, those can be added together, subtracted from the sample amount to give you the amount of oxygen. This is showing it in a block diagram. So what I was talking about doing, if pictures help, if you have the mass of the sample, right, and you burn your sample in O2, you get the mass of CO2 and the mass of water. You guys with me? And then I used the calculation on the previous slide to go from mass of carbon to moles of carbon, and then I can use the mass of H2O to go to a mass of hydrogen and moles of hydrogen. If I just have carbon and hydrogen, then I can go right to the empirical formula. Okay? If I have oxygen, then what I do is I take these two masses and add them together, and I subtract them to find the mass of oxygen from the mass of the sample, right? And then once I get the mass of oxygen, I find the moles of it. Then I have the moles of all three, and then I do my ratio to find the smallest whole number ratio. Cool? Right? So this is the things we've been doing on the previous sections put into a real world situation, okay? An analyzer that's commonly used. So now we need a problem. If 2.5 grams of butyl butyrate contains CHNO with a molar mass of 144.21 grams per mole, yielded 6.1 grams of CO2 and 2.5 grams of H2O upon combustion analysis, what is the molecular formula? Okay, So that means that we need to get to the moles of carbon, hydrogen, and oxygen. Okay? We need to get to the moles of carbon, hydrogen, and oxygen. And so let's get to the mass of the carbon and hydrogen so we can find the mass of the oxygen. And then we'll take all the masses and convert them into moles. Does that work? Yeah? So how do I get to the mass of carbon from CO2? I have 6.10 grams of CO2, right? What's the first thing I'm going to do? Figure out the molar mass of CO2, 12 plus 32, 44. In dimensional analysis, when you're going from one compound to another, or from one compound to a single element in it, always include the mole ratio, even if it's 1 to 1. Okay? It's just a good habit. Alright? Alright. So now I've got moles of carbon. If I do this calculation right now, am I going to need this number? If I completed it the way it is? I will, but we'll go back to that. And then times 12.01 grams per mole. Oops. Yep. So how many grams carbon? Or how many grams carbon? One 1.66? 1.6667. All right, we'll go there. Cool. All right. How about the grams of hydrogen? So I've got 2.5 grams of H2O. I'll let you guys be working on that. How many moles of hydrogen per mole of water? 2 moles. So we use 1 to 1 up here, right? What's the ratio for carbon, or excuse me, hydrogen to oxygen? Or 2 to 1 for hydrogen and water. So be sure and include that. Cool. And one gram per mole for hydrogen. All right, and we got that value. 0.279 grams of hydrogen. Anybody agree with that? Confirm that? All right. So now, if I have 2.50 grams of a compound, right? We'll call it compound BB. Okay? If I have 2.5 grams of that, and this compound contains, well, and let me do it this way so maybe it's clearer. Let's call it CHO, X, Y, and Z. Okay? Because that's what we're really doing. Okay, we're finding X, Y, and Z. And so I have 2.5 grams of that. And I subtract from that 1.67 grams of carbon plus 0.279 279 grams of hydrogen. For some reason I'm having struggles with that hydrogen today. All right, what does that give me? This equals the grams of oxygen. Anybody got that number? 0.551. Cool? Yeah. All right. So now we have grams of all three. What are we going to do? We now have a now that we've done this part, what math problem do we have? We just did. And finding the empirical formula, and then from the empirical formula, find the molecular formula. All right, so we just did both of those problems. So see if you can finish this one up from that place. Okay? You've got the grams. Convert those grams to moles. Find the mole ratio, the empirical formula, and then the molecular formula. See if you can finish it. Your homework will have a number of these problems in it. So. Cool? Exciting? Especially now that you know how to do them. So I pulled up the mole ratios that are appropriate. You guys are there yet? So, I mean, I always like to think of it as that, you know, C to 0.138, H to 0.278, and O to 0.035. Okay? I like to think of it that way, and then I do my division to find that relationship to get them to whole numbers. So what are you going to divide by? 0.035, the smallest, right? The smallest. And so if you divide that out, you come up with C4H8O. That's the empirical formula. All right. And then the last step is to take the molar mass given in the question, 144.21, and divide that by the empirical formula mass, which is 72. And so you get 2, so the final formula is C8H16O2. Cool? All right. So the next 10 or 15 slides are all review. If you'd like to go back and look at those, we're starting chapter 4 on Friday, right? Starting chapter 4.